Welcome to The Explainer. Today, we're going to break down one of the most fundamental ideas in, well, pretty much everything, the function. And trust me, once you really get what it is, you'll start to see the hidden rules that run the world all around you.
So, let me ask you this. What could possibly connect student grades, the GPS on your phone, and a block of computer code? It seems kind of random, right? But believe it or not, they are all built on the exact same powerful idea, a simple way of describing relationships that's key to how we make sense of the world. All right, here's how we're going to tackle this. We'll start with a basic idea of a function as a simple rule. Then we'll look at its core ingredients, check out some special types, see how to run them in reverse and chain them together, and then finally, we'll see why functions are basically the heart of all computer code. So, to really wrap our heads around what a function is, let's start with something super familiar, a real-world example we've all been through: getting grades in a class. The easiest way to think of a function is as a rule. It takes an input and it assigns an output. That's it. In this case, the input is the student and the output is their grade. Adams gets an A, Chow gets a C, you get the picture. This simple table, it's a perfect function in action. Every student is assigned exactly one grade. And that, right there, is the non-negotiable golden rule. For anything to be a function, every single input has to have one and only one output. A student can't get both an A and a C for their final grade, right? It's that single, clear-cut assignment that makes the whole idea work.
Okay, so we've got the basic concept down. Now let's get a little more specific and break this thing down into its three essential parts. You can think of this as the official parts list for any function you're ever going to encounter.
First up is the domain. This is just the complete set of all the things you're allowed to put into the function. So in our classroom example, the domain is simply the list of all the students. Easy enough? Next, we have the codomain. Now, this is the set of all possible outputs. It's the entire universe of answers the function could give you. For our students, the codomain would be all the possible grades they could get, from A all the way down to F. And that brings us to our third piece, the range. The range is the set of outputs the function actually spits out. So take a look here. The grade D isn't in the range. Why? Because even though D was a possible grade, it was in the codomain, nobody actually got one. The range is what you really get. Okay, so not all functions are created equal. We can actually classify them based on how they connect their inputs to their outputs. And these classifications give them some really unique and powerful properties. We've got two big ones here. A function is called one-to-one if every single input goes to its own unique output. No sharing allowed. The perfect example is a student ID number. No two students can have the same one. Then, on the other hand, a function is onto if every possible output in the codomain actually gets used. Here's what that one-to-one idea looks like. See? Every item on the left has its own dedicated partner on the right. Nothing is shared. This is absolutely critical for things like unique identifiers or cryptography, where you need a clear, unconfused mapping. And here's an onto function. Notice how every single dot on the right side has at least one arrow pointing to it? Nothing was left out. It's like filling every seat in a movie theater. Every possible spot is occupied. The entire set of potential outputs is covered. So what happens when you get a function that is both one-to-one and onto? Well, then you've got yourself a bijection. This is kind of the gold standard of functions. It creates a perfect one-for-one correspondence between two sets. And that idea of a perfect bijective match? Well, that leads us straight to our next topic, the ability to actually run a function backward. See, if and only if a function is a bijection, we can create what's called an inverse function that perfectly undoes the original. And the reason it has to be a bijection is pretty straightforward. If it wasn't one-to-one and two inputs pointed to the same output, how would you know which one to go back to? And if it wasn't onto, you'd have some outputs with no input to return to at all. A bijection guarantees a clear path back. So we can go backwards, but what if we want to go forwards but through multiple steps? What if we want to hook functions together one after the other, like a little assembly line for our data? Well, that's called composition. Let's just visualize this. First, we take our starting input, let's call it A, and we feed it into our first function machine, which we'll call G. And out the other side comes the result, G of A. But we're not stopping there. We immediately grab that output, G of A, and we use it as the brand new input for a second function machine, F. And the final result of this whole chain reaction is f of g of a. We write this with a little circle, and the key thing to remember is that you always work from the inside out. This whole process of applying one function to the result of another one, that is function composition.
Okay, that was a lot of theory. So let's bring this all back home and answer that question from the beginning. Why does any of this matter in the real world of computer code? Because this is what a function looks like in the wild. When a programmer types this exact line of code, they are literally defining a function. They're saying, I'm creating a rule called floor. Its domain is floating point numbers, and its codomain, the type of answer it promises to give back, is integers. It's the exact same idea. And really, that's the big secret. Functions are the Lego bricks of programming. Every single complex app on your phone, every website you visit, it's all just built by defining a bunch of simple functions that do one little thing well, and then composing them, chaining them together to create incredibly complex behaviors. An algorithm is just a fancy recipe of functions. So the real takeaway isn't just about math or code. It's that functions are the hidden pattern for almost any cause and effect relationship. A coffee machine is a function. It takes in beans and water and outputs coffee. A calculator is a collection of functions. Once you know what to look for, input, rule, output, you start to see that our world is, quite literally, run by them.